In this video, I will provide a brief introduction to inferential statistics, the use of point estimates and confidence intervals, and also provide some SPSS illustrations. As discussed earlier in this course, we are oftentimes not as concerned with studying the characteristics of samples as we are in making inferences about the characteristics of populations. Inferential statistics is concerned with drawing correct inferences about population characteristics, called parameters, based on sample statistics. In short, we draw a sample from a population, compute sample statistics on our variable, and then attempt to make inferences about the behavior of our variable in the population from which the sample is drawn. For example, a researcher might compute a sample mean and standard deviation for a variable such as height or intention to vote in the next election, and then use those statistics as estimates of height or intention to vote in the next election within a population. So basically, our sample statistics are used as estimates of population parameters. As another example, a researcher might compute the proportion of people voting for candidate A and for candidate B in a sample of prospective voters. The sample proportions are used as estimates of the population proportions of people intending to vote for those two candidates. In short, the researcher may attempt to draw an inference about the population proportions based on the sample proportions. Now, with our sample estimates of population parameters, there is always a degree of uncertainty with them. Now, there are two types of sample estimates of population parameters: point estimates and interval estimates. The latter are typically referred to as confidence intervals. A point estimate is a single estimate of a population parameter. This can be a mean, a standard deviation, a correlation coefficient, proportion, and so forth. An interval estimate, also referred to as a confidence interval, provides an estimated range wherein which a true population parameter might fall. So let's say our polling researcher computes from her sample data the following proportions of voters intending to vote for candidates A and B. Where candidate A, the proportion is 0.33, candidate B, the proportion is 0.67. So these are point estimates of the population proportions. Note, if we were to multiply these proportions by 100%, we would see that 33% of the prospective voters intend to vote for candidate A, and 67% would be intending to vote for candidate B. Now let's say the researcher establishes the following interval estimates for the proportions. Let's say the researcher forms a 95% confidence interval for around the proportion associated with candidate A, and the interval ranges between a lower bound of 0.15 and an upper bound of 0.51. And candidate B, the confidence interval ranges between 0.49 and 0.85. So these are estimates of a range of values where the true population proportion might lie. Note, if we were to multiply these proportions by 100%, we could say that the estimated percentage intending to vote for candidate A is between 15% and 51%, and the estimated percentage intending to vote for candidate B is between 49% and 85%. Now let's say our researcher computes the sample mean for a variable. Let's call it intention to vote in the upcoming election, which we're going to treat as an interval variable. The sample mean, let's say the mean is equal to 3.22, would be considered a point estimate for the population mean. The researcher might also form a 90% confidence interval around the sample mean. Let's say the 90% confidence interval ranges between a lower bound of 1.22 and an upper bound of 5.22. So this would be an interval estimate of the population mean. The estimated population mean is estimated to fall between 1.22 and 5.22. Keep in mind, and this is an important point, a confidence interval is only an estimate of the population parameter. This does not mean that the actual population parameter has to or necessarily falls inside the interval. This is just one interval that can be formed from really an infinite number of samples that can be drawn from the population. So the statements 90% confidence interval and 95% confidence interval reflect an effort to build interval estimates where we have a certain degree of confidence that they may overlap with the true population parameter value. All things being equal, we can have greater confidence in our interval estimates when it's 95% as opposed to 90%. We'll have greater confidence in our interval estimate when it's 90% as opposed to 68%. In short, the larger the confidence interval in terms of percentage coverage, the greater the confidence we have in our interval estimates of a population parameter. So this is to give you sort of a visual of what I'm talking about. When we draw out a sample and compute a point estimate, it could for a given sample, it might appear right here. And we could form an interval estimate around that point estimate. So this is the confidence interval, this is the lower bound and the upper bound, and this would be the point estimate. Now if I put that sample back into the population and then draw out another sample at random, then I might end up with a point estimate here and a confidence interval ranging from the lower bound here to an upper bound here. If I kept doing this repeatedly, let's say I did this 100 times, if I was forming 90% confidence intervals, then I would expect that 90% of the time the confidence intervals that I form would overlap with the true population parameter, which is falling at this point. So that's the basic idea. So when we say that there's a 90%, when we form a 90% confidence interval, that doesn't mean that there's a 90% chance that the actual population value falls inside the interval, but rather there's a 90% chance that the interval that we form overlaps with the true population parameter. Here's an example where we're forming a 95% confidence interval. And this, let's say with repeated sampling, you can see that the width of the intervals is larger, okay, and that's capturing, and so we have actually a greater probability that our interval, any interval that we form based on our sample data, will be greater than, will overlap with the true population mean relative to the 90% confidence intervals. So if we form 95% confidence intervals, what that means is that there's a 95% chance that any interval that we form will overlap with the true population parameter. But that does not necessarily mean that that the true population parameter falls within the interval. Only that there's a 95% chance that the interval that we form from whatever sample would overlap the true population value. Now, the accuracy of point and interval estimates of population parameters depends on sampling. All things being equal, sample estimates of population parameters will be more reliable, that is, they'll contain less uncertainty when drawing larger as opposed to smaller samples from a population. Uncertainty associated with population estimates is referred to as sampling error, and the sampling error associated with a population estimate is indexed by the standard error. There's actually several indices. There's the variance error and the standard error, but we're going to focus on the standard error. In short, sampling error tends to be smaller when your samples are larger. That also will mean then that, or by extension, that means that the standard errors associated with your estimate will be smaller. It's also important to note that the way in which you sample can have an impact on your estimates. So all things being equal, a random sample from a population is better than a non-random sample. With non-random sampling, you oftentimes get biases in terms of the point estimates and interval estimates, and so what that produces are inaccuracies in estimating the population parameters. So if you happen to be collecting data using convenient samples or some type of non-random sampling scheme, you have to, when you're discussing your results, you need to include that caveat when making your inferences about population parameters. So here's a data set. I've got 3 variables and I've got 20 cases. I've got intention to vote, preference for candidate, which is basically a nominal variable representing a preferred candidate, where 0 represents candidate A, 1 represents candidate B. The intention to vote variable we're going to treat as an interval variable reflecting intention to vote in the next election. And then the Paul party variable is coded 1 for Democrat, 2 for Republican, and 3 for independent. So we're going to start by finding the sample mean and 95% confidence interval for the intention to vote variable. Alright, so what I'm going to do actually at this point is open up SPSS and walk you through it. So here we have our data file. It's a little hard to see, but there's the intention to vote variable over here, preference for candidate and political party. If I go under variable view, you'll see that we have intention to vote as a scale variable, preference for candidate is nominal, and party identification is nominal as well. And you'll see the values for 0 and 1 for preference for candidate, party is denoted by 1, 2, and 3 for Democrats, Republicans, and Independents. So basically, if I want to start off by computing a confidence interval around my intention to vote variable, then what I'll do is I'll go to Analyze, Descriptive Statistics, go to Explore. And all this information is found in the PowerPoint. But again, I just wanted to walk you through it so that you'll see this stuff in action. So I'm going to move my intention to vote variable over to the dependent list where it says Statistics. Right here, this is where it says confidence interval for the mean. So the default is 95%. If I wanted to form a 90% confidence interval, I could do that. If I wanted to form a 68% confidence interval, I could do that. I'm going to leave this on 95%. And I'll click on Continue and then on OK. And so in terms of the output file, you'll notice that we get the intention to vote variable. The mean for that variable is 5.7. The standard error, which is indexing the amount of sampling error associated with our estimate, is 0.603. And then the 95% confidence interval is 4.43, roughly 4.438 to 6.962. So basically, if I was kind of writing this out, I would say 95% confidence interval, I'll just use CI right here, is equal to, and then in parentheses, I would have 4.438, comma, and then 6.962. So 6.962, or yeah, 6.962, and then in parentheses. So that's commonly how you would write this out right here. So let's say I wanted to form a 90% confidence interval. I'll do that too. So I would go to Analyze, Descriptive Statistics, Explore. Under Statistics, I'll just change this to 90%. Press Continue, and then on OK. And so now I got my 90% confidence interval. You'll see that the mean and standard error are exactly the same, but you'll see that the values for the confidence interval basically are a little bit narrower. And that's actually a bad thing because that means that you're covering less of the sampling distribution. So basically the 90% confidence interval ranges between a lower bound of 4.657 and an upper bound of 6.743. Alright, so now let's look at going back, and let's look at the preference for candidate. So let's say I want to determine, I want to form confidence, I want to compute the proportion within my sample being used as an estimate of the population proportion of those people preferring candidate B. And candidate B was, going back and looking at our data here, candidate B was coded 1, candidate A was coded 0. So what I'll do is I will go to, so this is a nominal variable, and so when dealing with nominal variables, it only makes sense to talk in terms of frequencies and proportions, or percentages. So what I'll do is I'll go to Analyze, Non-Parametric Tests, One Sample, and I'm just going to reset this so I can illustrate this. So basically, under Objective, it should say Automatically Compare Observed Data to Hypothesize. Under Fields, reset, I should have, oops, preference for candidate listed over test fields, because that's the variable that I'm going to be working with. Under Settings, I'll click on Customize Tests, and then compare observed binary probability to hypothesize. So this is a binomial test. I'll click on Options, and I'll click on Klopper, Pearson, Exact. And then down here, I will click on Specify Success Values, and basically the success value is 1 because that's the group that I'm looking at in terms of the proportion of folks favoring candidate B. So value of 1 was associated with candidate B. I'll click on OK. Under test options, I want to make sure this interval is set at 95%. If I was generating a 90% confidence interval, then I would just use this little button right here to move it to 90%. So basically this little button right here is to change the percentage. So at this point I'll press run, and when I scroll down I get this box, and to get the actual proportion associated with support for candidate B and also the confidence interval, I'll double click on this and this box will come up. So basically down here where it says hypothesis summary view, or in the view, I'm going to click this little arrow and then go down to confidence interval summary view. And so now you'll see that I have the proportion, so you can see probability for preference for candidate B is 0.55. So the estimated proportion of the, or within the sample, 55% of the distribution preferred candidate B. So the estimated population proportion is 0.55, or in percentage terms, it's 55%. The confidence interval ranges between a lower bound of 0.315 and an upper bound of 0.769. So if I multiply these values by 100%, then I would estimate that the population proportion favoring candidate B would range between 31.5% and 76.9%. Now let's say I want to look at estimating the population proportions associated with candidate A. I would go back to non-parametric tests, one sample, and everything would be exactly the same except that under settings I would go to choose tests. I would go back to customize tests, have this box clicked, and under options, and I would click 0. Actually, I would get rid of the 1 and type in 0 because I'm going to be estimating the proportion of folks favoring candidate A. So then I'll click on OK and then run. And so here's my box again. And so I'll just double click here, go to confidence interval summary view, click here. And so now you'll see that the proportion of my sample favored candidate A is 0.45, which it makes sense because the proportion favoring candidate B was 0.55, and if you add those together you get basically 100% of the sample. So if we multiply this by 100%, then we would say that 45% of the sample favor candidate A. That's my point estimate for the population value. The interval estimate ranges between 0.231 and 0.685. So if I multiply these values by 100%, then I would estimate that the proportion within the population favoring candidate A would be about 23.1%, between 23.1% and 68.5%. So let's look at our next variable. Let's look at party identification. So if I want to come up with the estimates for the proportion of people who are Democrats, Republicans, and Independents, then basically I would use the same general strategy. I would go to non-parametric test, one sample. Under fields, I'm going to move this variable over and put political party in instead. Under settings, I would go to for choose tests. Under options, I'll start off with the Democrats. I'm going to remove this and type in 1 because the Democrats were coded 1. Click on OK, and then basically, under test options, make sure this is set at 95%, and then I will click on run. So when I double click on this and click on confidence interval summary view, you'll see that the proportion of Democrats in the sample was 0.55. So in other words, 55% of the sample was comprised of Democrats. That's my point estimate for the population percentage. In terms of the confidence interval, it ranges between 0.315 and 0.769. So if you multiply by 100%, we would estimate that the population proportion of Democrats was 31.5% to 76.9%. Now let's look at the Republicans. So I'll go to Analyze, Non-Parametric Test, one sample. and under choose tests, I'm going to type 2 in down here. So I'm going to get rid of the 1, type 2, click OK and run. Double click here, go to confidence interval summary view. So the proportion in my sample of Republicans was 0.3, so that's 30% of the sample was comprised of Republicans. Again, that's my point estimate for the population value. The 95% confidence interval ranges between 0.119 and 0.543. So we're estimating that in the population between 11.9% and 54.3% is comprised of people identifying as Republican. And then in terms of independence, we would just go to analyze, again, non-parametric, one sample. Under options, we would just type in, get rid of the 2, type in 3 for independence. Okay, and then run. We'll go back to the confidence interval summary here, and you'll see that basically the proportion in the sample of independence was 0.15, so basically 15% of the sample is comprised of independents. That's our point estimate. The estimated population proportion for independence was 0.032 to 0.379, so we're estimating that within the population the percentage of independents would be between 3.2% and 37.9%. So basically, those are two illustrations of the use of confidence intervals and how they are formed in relation to our point estimates. So basically, again, our point estimate is basically capturing a single estimate of a population parameter. The confidence interval is used to come up with an estimated range for the population parameter. So that concludes this introductory foray into inferential statistics.